General-purpose computing on graphics processing units is the use of a graphics processing unit, which typically handles computation only for computer graphics, to perform computation in applications traditionally handled by the central processing unit. The use of multiple graphics cards in one computer, or large numbers of graphics chips, further parallelizes the already parallel nature of graphics processing. Essentially, a GPGPU pipeline is a kind of parallel processing between one or more GPUs and CPUs that analyzes data as if it were in image or other graphic form. While GPUs generally operate at lower frequencies, they usually have many times more cores to make up for it and can, thus, operate on pictures and graphical data effectively much faster, dozens or even hundreds of times faster than a traditional CPU. Migrating data into graphical form and then using the GPU to look at it and analyze it can result in profound speed-up. GPGPU pipelines developed out of scientific computing history. General-purpose computing on GPUs only became practical and popular after California, 2001, with the advent of both programmable shaders and floating-point support on graphics processors. In particular, problems involving matrices or vectors, especially 2, 3, or 4-dimensional vectors, were easy to translate to a GPU, which acts with native speed and support on those types. The scientific computing community's experiments with the new hardware started with a matrix multiplication routine, one of the first common scientific programs to run faster on GPUs than CPUs was an implementation of Loop Vectorization. These early efforts to use GPUs as general-purpose processors required reformulating computational problems in terms of graphics primitives, as supported by the two major IPs for graphics processors, Opencl and DirectX. These were followed by NVIDIA's CUDA, which allowed programmers to ignore the underlying graphical concepts in favor of more common high-performance computing concepts. Newer, hardware vendor-independent offerings include Microsoft's Direct Compute and Apple Cronus Group's Opencl. This means that modern GPGPU pipelines can leverage the speed of a GPU without requiring full and explicit conversion of the data to a graphical form. Implementations. Any language that allows the code running on the CPU to poll a GPU shader for return values, can create a GPGPU framework. Opencl is the currently dominant open general-purpose GPU computing language, and is an open standard defined by the Cronus Group. Opencl provides a cross-platform GPGPU platform that additionally supports data parallel compute on CPUs. Opencl is actively supported on Intel, AMD, NVIDIA and ARM platforms. The dominant proprietary framework is NVIDIA CUDA. NVIDIA launched CUDA in 2006, an SDK and API that allows using the C programming language to code algorithms for execution on GeForce 8 series GPUs. Programming standards for parallel computing include Opencl, Opencl and OpenHUP. Mark Harris, the founder of GPGPU.org, coined the term GPGPU. OpenVideo was developed at University of Toronto during 2003 to 2005, in collaboration with NVIDIA. Microsoft introduced the GPU computing language F#, and the Direct Compute GPU computing API, released with the DirectX 11 API. MATLAB supports GPGPU acceleration using the Parallel Computing Toolbox and MATLAB Distributed Computing Server, as well as third-party packages like Jacket. GPGPU processing is also used to simulate Newtonian physics by physics engines, and commercial implementations include Havok Physics, FX and PHYSX, both of which are typically used for computer and video games. Close to Metal, now called Stream, AMD, ATI's GPGPU technology for ATI Radeon-based GPUs. C++ Accelerated Massive Parallelism is a library that accelerates execution of C++ code by taking advantage of the data parallel hardware on GPUs. Mobile computers. Due to a trend of increasing power of mobile GPUs, general-purpose programming became available also on the mobile devices running major mobile operating systems. Google Android 4.2 enabled running RenderScript code on the mobile device GP²U. Apple introduced a proprietary Metal API for iOS applications, capable of executing arbitrary code through Apple's GP²U compute shaders. Hardware support. Computer graphics cards are produced by various vendors, such as NVIDIA and AMD. ATI cards from such vendors differ on implementation of data format support, such as integer and floating point formats. Microsoft introduced a shader model standard to help rank the various features of graphic cards into a simple shader model version number. Integer numbers. Pre-DirectX 9 graphics cards only supported paletted or integer color types. Various formats are available, each containing a red element, a green element, and a blue element. Sometimes an additional alpha value is added, to be used for transparency. Common formats are 8 bits per pixel, sometimes palette mode, where each value is an index in a table with the real color value specified in one of the other formats. Sometimes 3 bits for red, 3 bits for green, and 2 bits for blue. 16 bits per pixel, usually allocated as 5 bits for red, 6 bits for green, and 5 bits for blue. 24 bits per pixel, 8 bits for each of red, green, and blue. 32 bits per pixel, 8 bits for each of red, green, blue, and alpha. Floating point numbers for early fixed function or limited programmability graphics. This was sufficient because this is also the representation used in displays. This representation does have certain limitations, however. Given sufficient graphics processing power, even graphics programmers would like to use better formats, such as floating point data formats, to obtain effects such as high dynamic range imaging. Many GPGPU applications require floating point accuracy, which came with graphics cards conforming to the DirectX 9 specification. DirectX 9 Shader Model 2.x suggested the support of two precision types, full and partial precision. Full precision support could either be FP32 or FP24 or greater, while partial precision was FP16. ATI's R300 series of GPUs supported FP24 precision only in the programmable fragment pipeline, while NVIDIA's NV30 series supported both FP16 and FP32. Other vendors such as S3 Graphics and XGI supported a mixture of formats up to FP24. Shader Model 3.0 altered the specification, increasing full precision requirements to a minimum of FP32 support in the fragment pipeline. ATI's Shader Model 3.0 compliant R5XX generation supports just FP32 throughout the pipeline, while NVIDIA's NV4X and G7X series continued to support both FP32 full precision and FP16 partial precisions. Although not stipulated by Shader Model 3.0, both ATI and NVIDIA's Shader Model 3.0 GPUs introduced support for blendable FP16 render targets, more easily facilitating the support for high dynamic range rendering. The implementations of floating point on NVIDIA GPUs are mostly IEEE compliant. However, this is not true across all vendors. This has implications for correctness which are considered important to some scientific applications. While 64-bit floating point values are commonly available on CPUs, These are not universally supported on GPUs. Some GPU architectures sacrifice IEEE compliance while others lack double precision altogether. There have been efforts to emulate double precision floating point values on GPUs. However, the speed trade-off negates any benefit to offloading the computation onto the GPU in the first place. Vectorization. Most operations on the GPU operate in a vectorized fashion. One operation can be performed on up to 4 values at once. For instance, if one color less than R1, G1, B1 greater than is to be modulated by another color less than R2, G2, B2 greater than, the GPU can produce the resulting color less than R1 ** R2, G1 * G2, B1 * B2 greater than in one operation. This functionality is useful in graphics because almost every basic data type is a vector. Examples include vertices, colors, normal vectors, and texture coordinates. Many other applications can put this to good use, and because of their higher performance, vector instructions have long been available on CPUs. GPU versus CPU. Originally, data was simply passed one way from a CPU to a GPU, then to a display device. However, as time progressed, it became valuable for GPUs to store at first simple, then complex structures of data to be passed back to the CPU that analyzed an image, or a set of scientific data represented as a 2D or 3D format that a graphics card can understand. Because the GPU has access to every draw operation, it can analyze data in these forms very quickly, whereas a CPU must poll every pixel or data element much more slowly. As the speed of access between a CPU and its larger pool of random access memory is slower than GPUs and graphics cards, which typically contain smaller amounts of more expensive memory that is very much faster to access. Transferring the portion of the data set to be actively analyzed to that GPU memory in the form of textures or other easily readable GPU forms, results in speed increase. The distinguishing feature of a GPGPU design is the ability to transfer information bidirectionally back from the GPU to the CPU. Generally, the data throughput in both directions is ideally high, resulting in a multiplier effect on the speed of a specific high-use algorithm. GPGPU pipelines may improve efficiency on especially large datasets or data containing 2D or 3D imagery. It is used in complex graphics pipelines as well as scientific computing, particularly in fields with large datasets like genome mapping, or where 2- or 3-dimensional analysis is useful, in particular at present biomolecular analysis, protein study, and other complex organic chemistry. Such pipelines can also vastly improve efficiency in image processing and computer vision, among other fields, as well as parallel processing generally. Some particularly heavily optimized pipelines have yielded speed increases of several hundred times the original CPU-based pipeline on one high-use task. A simple example would be a GPU program that collects data about average lighting values as it renders a particular view from either a camera or a computer graphics program back to the main program on the CPU, so that the CPU can then make adjustments to the overall screen view. A more advanced example might use edge detection to return both numerical information and a processed image representing outlines to a computer vision program controlling, say, a mobile robot. Because the GPU has fast and local hardware access to every pixel or other picture element in an image, it can analyze and average it or apply a Sobel edge filter or other convolution filter with much greater speed than a CPU, which typically must access slower random access memory copies of the graphic in question. GPGPU is fundamentally a software concept, not a hardware concept. It is a type of algorithm, not a piece of equipment. However, specialized equipment designs may even further enhance the efficiency of GPGPU pipelines, which traditionally perform relatively few algorithms on very large amounts of data. Massively parallelized, gigantic data-level tasks thus may be parallelized even further via specialized setups such as rack computing, which adds a third layer, many computing units each using many CPUs to correspond to many GPUs. Some Bitcoin miners used such setups for high-quantity processing caches. Historically, CPUs have used hardware-managed caches, but the earlier GPUs only provided software-managed local memories. However, as GPUs are being increasingly used for general-purpose applications, state-of-the-art GPUs are being designed with hardware-managed multi-level caches, which have helped the GPUs to move towards mainstream computing. For example, GT200 architecture GPUs did not feature an L2 cache. The Fermi GPU has 768 KB last-level cache. The Kepler GPU has 1536 KB last-level cache, and the Maxwell GPU has 2048 KB last-level cache. Energy efficiency. Several research projects have compared the energy efficiency of GPU with that of CPU and FPGA.